For decades, the electronics industry made a decision that saved time, reduced cost, and improved throughput. Sounds good, right? But it also introduced a reliability risk that, in many cases, wouldn't show up until months or even years later. More on this in just a moment. Stick around.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Konrad.
Welcome, or hopefully welcome back to Reliability Matters. Before we get started, a quick note about today's episode and the next one. This and the next episode will be solo episodes, no guests. I'm going to use this time to take a deeper dive into a topic that has shaped the reliability of electronics assemblies for decades and continues to challenge us today: post-reflow cleaning. This is part one of a two-part series. In this first episode, we're going to go back in time, because to understand where we are today and why cleaning has become such a debated topic, we need to understand how we got here. Today, if you walk into most electronics manufacturing facilities, you'll find a mix of processes. Some assemblies are cleaned, some are not, relying entirely on so-called no-clean processes. But it wasn't always this way. If you go back in history, all the way through the 1980s, cleaning wasn't optional. It was standard. It was expected, and in many cases, it was considered absolutely essential. Before the early 1990s, nearly all circuit assemblies were cleaned after soldering. Not some, not most, nearly all. The reason was straightforward. Most fluxes used at the time, particularly rosin-based fluxes, left behind residues that were visible, chemically active, and potentially reliability threatening. These residues could be ionic in nature, hygroscopic, meaning they attract moisture, and electrically conductive under the right conditions. Left on the board, they posed real risks. So the industry responded with a consistent approach: clean everything. And they had a very effective way to do it: solvent-based cleaning. The dominant cleaning agents at that time were chlorofluorocarbon-based solvents, commonly referred to as CFCs, namely 1,1,1-trichloroethane and specialized freon-based solvents. These solvents were extremely effective. They were non-flammable, chemically stable, highly efficient at removing flux residues, and compatible with a wide range of materials. From a manufacturing standpoint, they were close to ideal. You could process assemblies quickly, achieve very high levels of cleanliness, and do it consistently, which meant reliability, consistent reliability. But there was a problem. In 1987, the global community came together to address ozone depletion. This effort resulted in an international treaty called the Montreal Protocol. Scientific research showed that CFCs were a major contributor to ozone depletion. When released into the atmosphere, they eventually break down and release chlorine atoms, which destroy ozone molecules. The implications were serious: increased UV radiation, environmental damage, and health risks. So action was taken. The Montreal Protocol did not ban CFCs overnight. Instead, it established a phased approach. For the electronics industry, this meant a gradual reduction in the use of CFC-based solvents over roughly a 10-year period, with the phase-out essentially complete by 1999 in developed countries. This created a massive challenge. The most effective cleaning solution available would be no longer viable. Faced with this, the industry had two choices: find alternative cleaning methods or reduce the need for cleaning altogether. What emerged was a shift in philosophy. Instead of asking, how do we clean better, the industry began asking, how do we eliminate the need to clean? That shift led to the development and rapid adoption of no-clean flux chemistries. No-clean flux was designed to leave behind minimal, benign residues that would not need to be removed, at least in theory. These fluxes were formulated to reduce ionic content, minimize visible residues, and lower chemical activity after reflow. For many applications, particularly commercial electronics, this approach was very attractive. It reduced process steps, lowered costs, increased throughput, and eliminated the need for new cleaning equipment. To understand why this worked, at least initially, we need to consider the design of circuit assemblies at that time. Most components were through-hole. Surface mount technology was still emerging. Component spacing was relatively large and standoff heights were very generous. These were not densely packed assemblies. There was space, lots of space, and that space reduced the likelihood that residues would create unintended electrical pathways. And it made any remaining residues less problematic from a reliability standpoint. As no clean flux gained traction, adoption followed a predictable pattern. IPC Class 1 and Class 2 assemblies, primarily consumer and commercial electronics, widely adopted no-clean processes. In many cases, cleaning was eliminated entirely. However, IPC Class 3 applications, such as aerospace, medical, and military electronics, took a different approach. These applications demanded the highest level of reliability, where
failure is not an option.
Failure is not an option. As a result, many Class 3 manufacturers continued to clean, even as no-clean processes became popular. And this is where something important happened. When the industry adopted no-clean processes, it wasn't just a decision to leave flux residues behind, it was a decision to stop removing all contamination from the assembly. That includes not just flux residues, but a wide range of other contaminant species introduced throughout the manufacturing process. At the time, that risk was not fully understood, because flux is only part of the story. On a typical circuit assembly, potential contaminants include solder paste residues beyond flux activators, board fabrication residues from PCB manufacturing processes, handling contaminations such as fingerprints, skin oils, and salts, environmental contaminants like dust and airborne particles, ionic species introduced during the soldering process, and residues from solder mask and laminate materials. Each of these contaminants can contribute to reliability risks, especially when combined. Individually, some of these residues may seem insignificant, but collectively they can create conditions that lead to failure, particularly in the presence of moisture, electrical bias, and elevated temperatures. At this point, it's worth taking a moment to explain how electrical chemical migration, or ECM, actually occurs. This is not a theoretical risk. It's a well-understood failure mechanism, and it requires three conditions to exist, all at the same time. First, ionic contamination. These are residues that can dissolve into an electrolyte. Second, moisture. This can come from humidity, condensation, or even microclimates within an enclosure. When moisture is present, it dissolves ionic residues and forms a thin electrolyte layer across the surface of the assembly. And third, electrical bias, a voltage difference between adjacent conductors. When these three conditions are present, ECM can begin. The ionic residues dissolve into the moisture layer, forming a conductive solution. Under an electrical bias, metal at the anode begins to dissolve into metal ions. These ions migrate through the electrolyte toward the cathode. As they reach the cathode, they are reduced and deposit as metallic material. This leads to two primary failure mechanisms. The first is parasitic leakage. Before any visible structures form, the electrolyte itself can conduct current between adjacent conductors. This results in leakage currents that can cause signal distortion, parametric drift, premature battery failure, and intermittent failures. These issues are often difficult to diagnose because there is no obvious physical defect. The second, and more dramatic, is dendritic growth. As metal continues to deposit at the cathode, it begins to form tree-like conductive structures called dendrites. These dendrites grow progressively across the surface, extending from one conductor toward another. Eventually, a dendrite can bridge the gap between conductors and create a hard short. At that point, failure is no longer intermittent. It becomes catastrophic and can even lead to a fire. What makes ECM particularly challenging is that it is time-dependent. It may begin as parasitic leakage, subtle and intermittent, and then evolve into dendritic growth and a permanent short. This means a product can pass initial testing and still fail in the field under the right environmental conditions. And it all comes back to contamination. Without ionic residues, ECM cannot occur. But once contamination is present, all it takes is moisture and electrical bias for the process to begin. So now we have the setup. In the 1990s, the industry reduced or even eliminated cleaning. No clean flux became widely adopted, mostly in consumer and commercial applications, and at the same time, circuit assemblies began to evolve. As we move toward modern times, components become smaller, pitch spacing decreases, component densities increase, and standoff heights shrink. Surface mount technology becomes dominant, and we begin to see widespread use of QFNs, BGAs, chip-scale packages, and other low standoff devices. Now, the same residues that were once relatively harmless become far more problematic. They are trapped in tight spaces, challenging to remove, and more likely to create unintended electrical pathways. At the same time, electronics are no longer confined to controlled environments. With the expansion of IoT and advanced electronics, assemblies are now deployed into high humidity environments, temperature cycling conditions, outdoor applications, automotive systems, and industrial environments. In other words, environments where moisture and contaminants are expected, not occasional. Harsh environments combined with miniaturization in higher component densities dramatically lowers the tolerance for any residue left on the assembly. So let's connect the dots. We have a shift away from cleaning, an increase in residual contamination, a trend toward miniaturization, higher component densities, and a rapid expansion into harsh operating environments. Individually, each of these changes may seem manageable, but together they create a perfect storm, a delayed reliability risk, a time bomb. In this first episode, we've looked at how the industry transitioned from a clean everything approach to one where cleaning became optional, driven largely by environmental regulation, enabled by no-clean chemistry, and supported by the design characteristics of assemblies at the time. But as we've seen, the conditions that made no-clean viable have changed dramatically. In part 2, we'll bring this discussion into the present. We'll look at what cleaning actually means today, how we define cleanliness, why traditional assumptions about no-clean are being challenged, and what best practices look like in modern electronics manufacturing. Until then, I'll leave you with this thought. If you stop removing contamination, it doesn't stop existing. It just waits, and eventually, under the right conditions, it becomes a problem. Well, that's another wrap on another episode of Reliability Matters. Thanks for being here. If you haven't already, hit that subscribe button so you don't miss future episodes. A big thanks to PCB Chat from the Printed Circuit Engineering Association at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Got a question or an idea for a future episode? We'd love to hear from you. Visit reliabilitymatterspodcast.com to suggest a future topic or just to learn more about the podcast. Thanks again so much for being here. I appreciate you. Until next time, keep learning, keep doing it right, and remember, reliability matters. I'll see you again soon.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.